So in this podcast, I wanted to basically go over some chapter 6 problems, work some more out. Reading through some of your journal entries, I felt like one of the things I could do is maybe work out some more problems. So I'll start from here on out, kind of going through the chapters, adding little reviews. Okay. And so here's the first one, and I just pulled up some problems here. Let's see if I have these here. Well, here's the first one. Let me really quick pull up the other one. Okay, here it is, worksheet 6.1. I'm just going to work out some of these problems here. I think that might help you. The first one I want to do is just one of these conversions right here. And we're going to convert from joules to calories. Okay, so we have 3.55 times 10 to the 4th joules, and we want to convert this to calories. Okay, first of all, your conversion you'll use 1 calorie equals to 4.814 joules. Okay, so now this conversion is really not too hard. So we're going to start off with our number that we have, which is 3.55 times 10 to the 4th joules. Okay, we want to cancel out joules, so we're going to put the 4.814 joules at the bottom, so they'll cancel out here, and 1 calorie at the top because that's what we're trying to get. Okay, so all we need to do is divide this out, and you should get about 8.48 times 10 to the 3rd calories. Okay, so a little energy conversion there. Okay, let's look at the next one. The next one, let's just sort of walk this through. There's not really a workout. It's just let's talk about this. So here it says to identify the following energy exchanges as primarily heat or work. So we decide, are they talking about heat or work here? And determine the sign of internal energy. In your book, I do want to have a side note. They have internal energy is labeled as E or delta E. And eventually something this textbook does only. In thermodynamics, it's actually always labeled as delta U. So if you see delta U, that's delta E in your book. Okay. So remember that delta U or delta E is Q plus W. Okay. So sweat evaporates from skin. The skin is cooling. Okay. So we have to look at what is our system. Our system, it says, is the evaporating sweat. So we need to see what is the sweat doing. We don't care that the skin is cooling because that's not our system. Okay. Our sweat is evaporating. So for evaporation to occur, that means we go from a liquid to a gas. Okay. Anytime you're becoming more gas-like, that means you need heat energy in order to do this. So if you need heat, that means heat is going into the system, so it's a positive. Okay, and we're mainly talking about Q or heat, right? Because we're talking about a temperature change. So that one is heat, and it's positive because it needs heat into the system to be able to evaporate. Let's look at B. A balloon expands against an external pressure. So the balloon is our system. Let's see what the balloon is doing. It's expanding, right? Okay. So what are we looking at here? We're looking at work. Okay. Right? Because we're looking at expansion. We're not looking at a temperature change. Now let's look. Does the balloon want to expand? Does it want to do work? No, so that's negative. Anytime you have a volume change by your system, then it's doing work. So it's a negative sign there. Okay? Our last one here, an aqueous chemical reaction is warmed with an external flame. Our reaction mixture is the system. Okay, so let's look. Our reaction mixture is being warmed. So there's heat being heat being put into the system. Okay, since it's going into the system, that's positive. We want heat. Okay, and so we're looking at mainly heat. We're looking at Q, and the sign is positive. Okay, because heat is going into the system. Now, what if the system was the flame instead? The flame is letting off heat, so that would be a negative, okay, because it's expelling heat. Okay, so the overall sign would be negative. Anyway, let's just be careful on these to look at exactly what your system is. Don't look at what everything else is doing. Look at what only your system's doing. Okay, let's look at number 3. A system releases 415 kilojoules of heat. Okay, so if it releases that much, is the sign positive or negative? It's negative because it's releasing heat, okay? It's getting rid of heat. And heat, is that Q or W? That's Q, okay? So let's come back over here. We already did number 2, so let's go to number 3. Okay, remember that delta U is Q plus W. Q then will be negative 415 kilojoules. Okay, let's see what W is. And does 125 kilojoules of work. Do we want to do work? No, so that's negative. So now we need to calculate the external energy here. So this would be negative 125 kilojoules. Okay, so let's add these together. We have negative 415 plus a minus 125. When you add these together, you should get negative 540 kilojoules of your internal energy there. Okay, so these problems are never really hard. I would say the hardest part is determining the signs right here and right here and here. Are we looking at a negative or positive? Because we're just adding together. I'm sure everybody can add and subtract, but determining the sign is the hardest part. Okay, let's do another one. Okay, go back here. How much heat is required to warm 1.5 liters of water from 25 to 100 degrees Celsius? Okay, so we're looking at Q, okay, and we have 1.5 liters of water from 25 to 100 degrees Celsius. Okay, so let's look at the formula for Q. Okay, Q equals to MC delta T. MC delta T. And let's write down all the information we have. We know the temperature initially was 25 degrees Celsius, and we're trying to warm it to 100 degrees Celsius. Okay, so here we can get the delta T. Remember, delta T is final minus initial. So if we put that in, that'd be 100 minus 25, which is 75 degrees Celsius. Okay, so we have delta T. Okay. C for water. I don't think it says it in the problem. Normally in a problem, they would give that to you or tell you where to look it up. But this is a chart in the book. C for water is 4.18. This is just a constant, okay? Divided by joules, grams, degrees Celsius. Okay, so we have C. Now we need M. Oops, I don't want to check it yet. I don't actually have it yet. I know that I have, what was it? The volume was 1.5 liters, okay? But I don't want volume, I want mass, okay? I want it in grams, because if you look at C will tell you the units you need here. I have a degree Celsius, which is good. Now I need a gram. Where the hint here is density for water is always 1 gram per milliliter. Okay, so we can convert this liters into grams by using the density. Okay, so first let's look here. This is in units of gram per milliliter. What do I need to do with this liter? I need to convert it to milliliter. Okay, so let's do that first. I put liter at the bottom to cancel it out, milliliter on top, right? So the conversion here, there's 1 liter, and how many milliliters? 1,000. Okay, now I have milliliter at the bottom. I want to cancel it out. And what's the final unit I want to go to? Grams. So here, do you see I have this convenient density here? So there's 1 gram per 1 milliliter. Okay, so that cancels out milliliters, cancels out liters, okay, and leaves me with a gram. So 1.5 times 1,000 is 1,500 grams of water. Okay, so now I really do have my mass of water. Let me change this here. So again, Q equals MC delta T. So Q equals M mass, which I just calculated as 1,500 grams. C is 4.18 joules grams degrees Celsius. And then our delta T we have here as 75 degrees Celsius. So you see our Celsius will cancel, grams will cancel, so our final unit will be in joules, the only unit left. So if we multiply this out, 1,500 times 4.18 times 75, okay, what do we get? You should get about 4.7 times 10 to the 5th joules. Okay, that is how much energy it's going to take to bring water from 25 degrees Celsius to 100 degrees Celsius, or actually specifically 1.5 liters of water. So it takes quite a bit of energy to do that. Okay, think about if we're boiling a giant pot, on your stove. Okay, if you had 1.5 liters of water you had to boil, that's going to take forever, right? And so it takes a lot of energy. Let's look at another problem, and this time instead of looking at heat or Q, let's look at work. So let's recall work equals to minus P, this is your external energy, change of delta V. And also remember when your units when you do this, so P is usually in atmospheres, and V is liters. So you're going to get units of liters atmospheres, which is not actually what you ever want. You want it in joules. Okay? So just know that 1 liter atmosphere equals to 101.35 joules. Okay, so that's our conversion there. Now let's look what our problem has. It says how much work in joules. They're always going to pretty much make you convert to joules, so you'll need that conversion there. Is required to expand the volume of a pump from 0 liters to 2.5 liters against an external pressure of 1.1 atmospheres. Okay, so here's our volume, here's our pressure. Let's write it all down. Okay, so our pressure, it said, is 1.1 atmospheres. Okay? Our volume initially is 0 liters. So we're starting out at 0 liters, and we want to go all the way to 2.5 liters. Okay? So how much did we change there? Our change in volume is 2.5 liters because it went from 0 to 2.5, so expanded 2.5. Okay, now let's put everything in. We have pressure and we have our delta V. Okay, so now work equals to minus, remember the minus sign right there, that could get you in trouble, 1.1 atmospheres multiplied by 2.5 liters. That's your change in volume. So when you do this, you multiply this out, you're going to get negative 2.75 atmospheres. Okay, or liters atmospheres. Okay, but remember, we don't want liters atmospheres, we want it in joules. So we're almost done, okay? We just need to convert it. So we know that 2.75, put our negative there, liters atmospheres. We want to cancel that out, so we're going to put liters atmospheres on the bottom. We know that one of those equals to 101.35 joules. Cancels out, so we multiply this out here, and we're going to get negative 280 joules. Okay, so to expand this from 0 to 2.5 liters, that's how much energy it takes. Okay, oh, and then with the external pressure. And what, just let me really quick, what does the external pressure mean? Okay, think about if you're putting pressure on something. Okay, that's like putting a weight against it almost. Okay, so if we have like a balloon and we want to expand it, we want to put oxygen into the balloon, but there's an external pressure of 1.1. Okay, that pressure is going to go against us. It's going to make it harder for the balloon to expand. Okay, so it's going to take a little bit more energy. So it's basically the pressure you have to overcome to expand the balloon. Okay, so that's sort of like the first half of chapter 6. Now let's go over sort of the second half. And let me actually do this in another vodcast so they're kind of separate a little bit.